Have you ever wondered why it is possible to make a stone skip water when us humans can barely cross a meter without sinking in? Well, believe it or not, some people such as Kurt Steiner, who detains the world record by making a rock skip 88 times, may have the answer to this question, and apparently it is not as magical as I wish it was. For the context of my reasoning, let the essence of stone skipping be that it is to throw a perfectly thin and circular stone at a body of water with an optimal angle, yet to be defined, at a large enough velocity, while giving the stone a spin and then watch how many times that stone bounces on water. How do all of these essential components make it possible for a stone to skip water? Firstly, by giving a spin to the rock, you are stabilizing the stone, and this effect is called gyroscopic stabilization. This means the greater the stone's angular velocity is, the greater its stability is in its particular orientation and position. Therefore, the angle between the stone and the water surface is somewhat constant during the whole process. Second, as of the angle, it was shown by a group of French researchers in 2004 that the optimal impact angle for all velocities was around 20 degrees. That is considering that no rebound was possible at an angle over 45 degrees. That is why it is important that the angle between the stone and the water surface remains constant throughout the whole collision process, since if initially thrown at 20 degrees, the stone will, at every single occasion, impact the water with the optimal angle. Now that we have seen how to throw the stone to make the rebound possible, what is going on during the collision itself? The reason why the stone rebounds on the water is explained by the principle of conservation of momentum. Plainly put, the principle says that there is no loss of momentum when there is an interaction between two bodies. Actually, there are external forces applied on the stone that makes it stop, such as frictional force with the water. That is why the stone stops at some point. However, neglecting these external forces, when the stone touches the water, it applies a downward force on the water, which applies an upwards force on the stone, called a lift force, and makes the rock rise. These opposing forces, which occur during the collision between the stone and the water, are explained by Newton's third law of motion. For every force that one object exerts on a second object, there is an equal but opposingly directing force that the second object exerts on the first object. Therefore, that is why the stone receives a force to launch again from the wave created by that collision. Now, since the lift force is essential in the rebound process, the collision time certainly has a large effect on the rebound itself. In fact, the amount of energy lost during a collision is directly proportional to the collision time. This is why the greater the velocity of the stone is, the less energy it loses, and therefore the longer it can go. All of this, as stated earlier, is assuming that the stone is launched at a large enough velocity and therefore receives a strong enough upwards force from the water so it balances against the total weight of the stone, or else it would sink. That is why it is practically impossible for us humans to run on water, because it will require a large enough initial speed so that the force we receive from the collision with the water balances our weight, which is fairly larger than the weight of a small stone. Now, the condition for the stone to bounce is written as a very complex equation. However, this equation goes above the complexity of my argument. Therefore, it is essentially saying that the ability of the stone to bounce depends on its diameter, its velocity, its mass, its impact and incident angle, and the density of the water. Therefore, by throwing a perfectly circular and thin stone at an impact angle of 20 degrees on a calm, large water surface at the highest velocity possible, you could be the next world record holder.